So, last day we have talked about the large signal characteristics of differential pair, and hopefully you can remember that behavior of this differential output voltage with respect to the differential input voltage. The variation is something like that. If the input voltage is large enough, then the output voltage gets saturated at minus ISS times RT, and when the input voltage is small enough towards negative infinity, then the output voltage gets saturated to plus ISSRT. Right. So you understand that whenever it is plus ISSRT and minus ISSRT, one of the transistor, one of the MOS will carry this entire current, and the other MOS will be cut. So that's why, suppose if V1 minus V2 is very large, in that case this M1 will get this entire current, and in that case the current that is flowing through this is ISS. This V out 1 is equal to ISSRT, and this V out 2 is equal to 0. Is equal to VDD. So therefore, if you just consider this V out 1, which is nothing but VDD minus ISSRT, and this V out 2 is equal to simply VDD, because there is no current flowing through this right hand side resistor RT. So therefore, your V out 1 minus V out 2 is equal to minus ISSRT. On the other hand, if V1 minus V2 is very less as compared to 0, suppose it is very large, magnitude wise large, minus V1 minus V2 is much less than 0. In that case, this M2, this transistor, this MOS will be on, and it will carry this entire current ISS, and M1 will be off, and in that case you can expect that this V out 1 is equal to VDD, and this V out 2 is equal to VDD minus ISSRT. In that case, the differential output voltage is equal to simply ISS times RT, right? And when this V1 minus V2 is equal to 0, that means this entire system is in equilibrium. In that case, this voltage and this voltage, they are the same. So that means we are applying the common mode voltage. In that case, this V out 1 is equal to V out 2, and that is equal to VDD minus RT by 2 into ISS. So therefore, in that case, this V out 1 minus V out 2 is equal to 0, right? So you are not interested in observing the behavior over here, neither over here nor over there, right? And this is the DC condition. That means your both of these two voltages, V1 and V2, they are same, right? And you observe the last day this variation, and the variation looks something like that. This square law variation, which is having this kind of shape. And you have also noticed that there is some maximum input fluctuation that we can have, and by calculation we have identified that maximum applied voltage, that delta V in 1, which is equal to square root of twice ISS upon mu n C of W over L. That means if your this difference between V1 minus V2, if that difference exceeds this value, if I call it like delta V in 1, then what happens? One of the transistor will enter into the saturation, and one of the transistor will be in cutoff. So therefore, what happens if this delta V in is greater than delta V in 1? Then no longer both of these two transistors will be there in the saturation, right? Because for the operation of this M1 and M2 as an amplifier, we want that both of these two transistors must be there in the saturation. So that condition gets violated when delta V in is greater than delta V in 1. So therefore, delta V in 1 is the maximum value of the applied voltage, I mean the maximum value of the differential voltage that you can have. So that we have discussed last day, the large signal analysis, and today we will observe the gain. We will calculate the gain of this differential pair, keeping in mind that the maximum differential voltage should be within the limit of delta V in 1. It cannot exceed delta V in 1, because if it exceeds delta V in 1, then no longer this particular pair will act as an amplifier. Okay. So we have done this one in the last day, this large signal behavior. So today we will start with this particular diagram. So what we are doing over here is that, suppose this M1 and M2, they are having some DC voltage and they are experiencing some equal and opposite excursion over here. So plus delta V minus delta V, because we understand that the input of these two MOS, they must expect some differential kind of signal, right? So initially they are writing on the same DC level, and then when one gate is experiencing some positive delta V over here, then the other gate must experience the negative delta V. That means the notion of differential signal is applicable. Now under this condition, we are interested in finding out what is the gain. That means your V out 1 upon V out 1 minus V out 2 upon V1 minus V2. So you know that this V out 1 is given by simply VDD minus ID1 times RT, and V out2 is nothing but VDD minus ID2 times RD. So what is your V out1 minus V out2? That is simply minus RD into ID1 minus ID2. And last day, hopefully you can you have observed what is that addition of this ID1 minus ID2 with respect to the V1 minus V, right? So that addition was something like that. If you can remember, it was like half mu1 Cox W over L, then V1 minus V2 multiplied to this entire factor, the square root of 4 ISS mu1 Cox W over L minus V1 minus V2 whole square. Okay, so you must argue that okay, obviously that square part, this V1 minus V2 whole square, that particular thing must be less than this one. Otherwise, the term inside this square root will become negative. That we don't want. So therefore, the condition is that V1 minus V2 square, it should be less than 4 ISS upon mu n Cox W over L. Because already you have seen in the last slide, you have seen that this delta V1 is equal to square root of twice ISS mu n Cox W over L. So what is delta V1 of 1 square? It's nothing but twice ISS by mu n Cox W over L, right? And here we find that this is basically delta V1 minus V2. This is basically delta V1 minus V2. So that square, it should be less than 4 ISS by mu n Cox W over L, because it has to be less than twice ISS by mu n Cox W over L. Now, if it is very less than that, 4 ISS by mu n Cox W over L, then what I can write that this expression ultimately reduces to V out1 minus V out2 is equal to this one minus RT by 2 mu n Cox W over L, this V1 minus V2, and then this part. That means we are observing the behavior in the vicinity of this origin, be close to that. That means we are allowing the small signal to be applicable. This V1 minus V2, that square, it should be much less than 4 ISS upon mu n Cox W inside this square. What is there? That means we are interested in observing the gain or the fluctuation over here, which is very much close to this particular equilibrium point, right? So under this condition, what I can do or what I can write is this V out1 minus V out2 is something like minus, then you have this particular thing mu n Cox W over L ISS times RT times V1 minus V2. Okay, so what is the gain? Basically this V out1 minus V out2 upon V1 minus V2, that should be the gain, right? So in the expression of the gain, what you have something, this one multiplied with RT. Apart from that, you have minus sign. So can you identify this particular thing inside this square root? You already studied the single stage common emitter amplifier. Yeah. So here in that particular case, the square root of mu n Cox W over L, what is that? Nothing but the GM of the individual transistor. Why? Because already you know that was the expression. One of the expression for GM was something like that. GM is equal to square root of twice ID mu n Cox W over L. That was the expression, right? And here, so what is that ID? ID is the DC current. DC current. Under DC condition, you can expect that both of these transistors will share equal amount of current, that is ISS upon 2. So therefore, this becomes GM of the individual transistor. It becomes ISS times mu n Cox W over L. Right? So what we find, the ultimately the gain expression, this AV, if I consider the mod out or considering this AV, this is nothing but it's close to minus GM times RT. But remember that GM, and for a single stage common source amplifier, that GMs are not same. I'll come to this later on. So it's something like minus GM RT, and that expression of gain we have obtained from the large signal analysis itself, because that expression, that particular expression, this one, V1, I mean ID1 minus ID2 is equal to this much. That expression we have obtained in the last day, right? From the large signal perspective, and we do the same thing from the small signal perspective today. Okay. So as you know, here ID1 minus ID2 already we have obtained this one. ID1 minus ID2 is equal to this one. Square root of mu n Cox W over L times ISS into V1 minus V2. That is quite obvious. Why? Because as you understand that V out1 minus V out2 is how much? Minus RT times ID1 minus ID2. And here V out1 minus V out2 is equal to minus of these times RT into V1 minus V2. If you compare, what is your ID1 minus ID2? your ID1 minus ID2 is nothing but the square root of mu n C of W over L ISS times V1 minus V2. And what is that V1 minus V2 here? So in that case, we have applied plus delta V in one case, in one gate, and the minus delta V in the other gate, so that V1 minus V2 is equal to twice of delta V. Okay, so this is the expression for ID1 minus ID2, the square root of mu n C of W over L ISS into 2 delta V. And you know that ID1 plus ID2 that is equal to ISS, the total current. We apply KCL, and from that, what you can get, ID1 is equal to ISS by 2 plus this part. Similarly, you can have the expression for ID2. Right. Is it okay?
ISS by 2 minus 2.
Yes. So now the point is that this ID1, what is that ID1? This ID1 is the total instantaneous current. That you have the DC part, and apart from that, you have the small signal part, small signal variation. And you have applied some positive delta V at the gate 1, and you have applied some negative delta V at gate 2. So therefore, you should expect that ID1 is greater than its DC value, and ID2 is less than its DC value. So ID1 is equal to ISS upon 2 plus this entire thing, and ID2 is nothing but ISS by 2 minus this entire thing. Okay?
The DC value of the ISS by 2.
Yes, because both of them are sharing equal current, and I am assuming that both halves of this differential pair, they are symmetry. Okay, so what I can write this one. So what I can write this ID1. I can always write this. I can always write this ID1 as this ID1 plus small ID1, right? The total instantaneous current ID1 is the DC current ID1 plus this the small signal part, small ID1. So this is your DC part, ISS 1 2. This is the DC part, and this is the small signal variation. Now since it's a NMOS, so therefore you must understand that this current variation, drain current, is nothing but the GM times the gate source ID is nothing but GM VGS. So therefore this part over here, this is nothing but, this entire thing is nothing but GM. So I can write this entire thing is nothing but GM1 times VGS1. This is a small signal part, GM1 times VGS1. Now what is your VGS1 here? What is VGS1? What is VGS1? Do you know what is VGS1? This is the GM times VGS1, right? What is the GM1? You can calculate. What is GM1? GM1 you know. What is GM1? What is GM1? This GM1 is equal to square root of, already we have calculated, ISS mu n C of W over L, that is GM1. And you know that this entire thing is GM1 times VGS1, this entire thing. So from that you can calculate what is your VGS1, get to source variation.
Source is the constant.
The source is not, so we will come to that. Source is not constant. We know that this entire thing is GM1 VGS1. This is the GM1 VGS1, right? So from that, if you would like to find out what is my change in VGS1, this entire thing is GM1 VGS1. So what is the change in VGS1? So this entire thing upon GM1, right? Now what is that? You know that this thing, now this thing, which I marked by this yellow, this part is basically your GM1, right? So gets cancelled. So what is the change in delta VGS1, or what is the change in VGS1? It's nothing but delta V. So the final conclusion is that delta VGS1 is equal to delta V. So you have applied some change at the gate, right? If I once again go back to this slide, what I find, I have applied some change at the gate of M1 and M2, equal and opposite change with respect to ground. This delta V plus delta V minus delta V is applied with respect to the ground. That means you have some beams here, and then you applied some plus delta V at gate 1, and you applied some minus delta V at gate 2. So gate 1 voltage becomes VNCM plus delta V, and gate 2 voltage becomes VNCM minus delta V. What I obtain is that if I apply some positive delta V change at the gate 1, this positive delta V change at the gate 1 is basically absorbed between between the gate and the source. So that means you applied some change over there plus delta V. So this change is absorbed between the gate and the source, keeping this source terminal constant. Source terminal at a fixed potential. So you apply some change there, and that change is absorbed between the gate and the source, so that the source potential is remaining at a particular voltage. That voltage doesn't get changed. This particular potential doesn't get changed. So that will help in calculating or in analyzing the small signal part in a much better way, much convenient. Why? Because if you know that this particular potential is held at a constant value, so therefore in the small signal model you can make it at a AC ground. If this particular point, if I call this point say point P, suppose this point is a point P. Now if this potential is held at a constant value, therefore I can always treat this point in the small signal analysis, I can always make it AC ground. Clear? And that will help in observing this entire circuit. Hopefully you can remember what we have done in our BJT based differential amplifier circuit. In that case, we have also applied this half circuit concept, right? Here also we will do this half circuit concept. We will also apply this half circuit concept here also. That means we will observe or we will analyze the left hand side of this circuit and the right hand side of the circuit separately, and accordingly we will find out the expression for the overall voltage gain. Okay. So Vp is set at a constant value. Fine. So if it is a half circuit, so if you apply half circuit concept, and let's assume that the current source that we have used, the tail current source, this is an ideal current source. Constant current is ideal current source. That means you understand that it's a constant current source means it will provide infinite impedance. Okay. So in the half circuit model, the circuit reduces something like that. You have applied, you have got these two MOS M1 and M2, and their inputs are V1 and V2, and we have applied some differential input over there, V1 and V2, and the outputs, corresponding outputs are Vout1 upon Vout1 and Vout2, and we would like to find out Vout1 minus Vout2 upon V1 minus V. And if I have this half circuit concept, then what I can do, I can break this. I can analyze this part first, and then I can analyze this part. Okay. If you observe this part, what is that? It's basically single stage common source amplifier. So what is your Vout1 upon V1? Simply minus GM1 times R2. If I have minus GMRT, or if you have two different GMs, then minus GM1RT, or let it be simply minus GMRT. What is your Vout2 upon V2? What is Vout2 upon V2? Similarly, minus GM2 upon RT. Now with GM1 is equal to GM2, what I can have Vout1 minus Vout2 is equal to minus GMRT to V1 minus V2. So therefore, what is the gain? The gain becomes minus GMRT. But remember that GM, and for a common source GM, these two GMs are not same. We'll come to that. So this is a very fundamental way to analyze this circuit, right? But since we have two such inputs, V1, V2, and you have two outputs, Vout1 and Vout2, so you can also apply the theory of superposition. And using that particular theory, you can also come to the same conclusion. But that analysis will be a little bit complicated one. But still, for the sake of completeness, we will also discuss this particular analysis. Using the theory of superposition, how can I calculate the voltage gain of this differential pair? So, as you know, for applying the theory of superposition, you have to apply one input at a time and keeping the other inactive, and then you have to find out the individual outputs. So here you have two outputs, Vout1 and Vout2, and you have two inputs. You have two inputs, V1 and V2, and you have two outputs, Vout1 and Vout2. Now the good part is that since the circuit is symmetric, so if you analyze the circuit from one angle only, then you can also apply this equivalence, and accordingly you can find out the other outputs for the particular other input, right? So we start from the considering that I have applied some input like V1, and we would like to find out what should be my V out1 and what should be my V out2. If you can do that, then the rest of the part will be just the opposite, right? Now what happens? Now if you apply only V1, that means I am applying V1 only, V2 is not present. That means V2 is at 0, inactive. I have applied only V1. So V1 is applied over here at the gate of this particular MOS, and V2 is not applied. I would like to find out what is my V out1 only. I am interested in finding out V out1 only, not V out2, only V out1. So you have applied the input over there at the gate of this MOS. So can you identify what kind of amplifier it is? What configuration? Common source with regeneration. So what is my regeneration resistance? Because you know that the source is not grounded for a MOS. Source is not grounded. From here to ground, you have the input resistance of this second MOS, M2. What is the input resistance of this MOS? Common gate stage, that is 1 upon GM. Right, 1 upon GM2 I can call it. So this resistance is 1 upon GM2 from here to ground. From source 1 to ground, we have a resistance equal to 1 upon GM2. So now we have applied some V in 1, some resistance over there, drain resistance RD, and some source resistance is equal to 1 upon GM2. Right? So what should my gain? The gain is nothing but minus of the resistance in between the drain and the ground divided by 1 upon GM of the amplifying device plus the source plus the resistance in between the source and the AC. From here to ground, what is the resistance? From here to ground, if you can observe this one, for a simple common source stage, you have this kind of thing, no? Just like this. So here we applied V in there, or V in 1. This one is RT, this one is RS, this one is VDD, and this is my output terminal, V out. Common source stage, so you must be having some phase inertia. That's why minus RT upon, because in that particular case we have neglected the your R0 channel condition, have simply neglected. So minus RT upon 1 upon GM1 plus 1 upon GM2. So that means V in 1 is acting alone, and we would like to find out V out. The next part is little bit complicated. The next part, we would like to find out V out 2 when V1 is acting alone. Right. That means V out 2 has to be calculated with the assumption that V1 is acting alone. So how does it look like? It looks something like that. It looks something like that. So it will be a little bit complicated. So let me just take this color. Yes, so now V1 is applied. V1 is applied to the gate of MOS 1, and we would like to find out what is my V out 2. How can I do that? So therefore, let's identify. Okay, this part we would like to find out the Thevenin equivalent model over here. We would like to find out Thevenin equivalent model over here. So what is the Thevenin equivalent model over here? Because forget about this ISS, because since it's a ideal current source, so I can consider that it's infinite resistance, open, simply open circuit. So don't get confused with this ISS. So what I have, so this part of the circuit, I'd like to find out the corresponding Thevenin equivalent resistance and Thevenin equivalent voltage, so that now I can once I identify the Thevenin equivalent voltage and Thevenin equivalent resistance, then this entire part can be simply represented or can simply be substituted by this V Thevenin and R Thevenin. Right. So how to do that? So for that, let's draw the small signal model. I've already drawn the final output, but how did you obtain this one? So that I have to show the small signal model. So what I have for MOS 1, for MOS 1, what you have between gate to source, you have VGS1, and between drain to source, you have GM1 times VGS1, right? that is for MOS 1. This is the drain terminal, and you have this resistance RT which is connected to AC ground. Right? Now remember that source terminal, this source terminal is the connection to the rest of the world. Right? So this is the terminal over here. And over here, as you understand, this is applied voltage. What is that voltage? That voltage is nothing but your V in 1. Right? Applied the gate. So I would like to find out, so the rest of the circuit is there. Rest of the circuit is there. So let me take some other color. So the rest of the circuit is there. Right? I'd like to find out, and there is a ground. I'd like to find out what is my open circuit voltage, right? And what is the resistance looking between these two. So what is the open circuit voltage? Remember, whenever we are performing this Thevenin analysis, so we have to identify that first of all, for calculating your this Thevenin voltage, you have to ensure that this circuit, this part, for which I am interested in finding out this Thevenin equivalent model, this part is disconnected from the rest of the circuit, right? And I would like to find out what is my open circuit voltage over here between these two terminals. Okay, so what I find, I am having this VGS1 between gate and source 1, this GM1 VGS1, this voltage dependent current source between the drain and the source of MOS 1, and you have this resistance RT which is connected between this RT which is connected between the drain and the AC ground. Okay.
V1 to VGS1.
Yes. So what is your V in 1? V in 1 is equal to VGS1 plus this voltage. Now the thing is that since this part of the circuit is disconnected from the rest of the world, so therefore this current has nowhere to go. This current has nowhere to go. This current, you cannot complete the loop. This current has nowhere to go because this part is not connected. So this GM1 VGS1 is equal to 0 for the calculation of this Thevenin equivalent voltage and Thevenin equivalent resistance. I am coming to the resistance part later on. So if GM1 VGS1 is equal to 0, that means your VGS1 equal to 0 because GM1 is not 0. So therefore this is 0. So what is this voltage? This voltage is nothing but your V in 1, that voltage. That is the Thevenin equivalent voltage, V in 1, V Thevenin. What should be R Thevenin? How to calculate R Thevenin? What is the procedure? For calculating R Thevenin, what you need to do? You have to kill all the independent voltage source. So what are the independent voltage source there? So you have this voltage source. So that must be absent. Independent voltage source, right? And then what you need to do? You have to apply some test voltage over there. You need to apply some test voltage over here. You apply some test voltage, let it be Vx. Measure the current, Ix. Find out the ratio, Vx upon Ix. That will give you the R Thevenin. Right? Now, had this been the case, if this is 0, if this is absent, that means what? This is basically grounded. So what is your VGS1? This is basically minus Vx. Right? VGS1 is equal to minus Vx, and that current is nothing but GM1 VGS1.
GM1 gates.
Right? So ultimately the resistance Vx upon Ix is nothing but 1 upon Gm. That is the Thevenin equivalent resistance. So with this understanding, now let's come back to the original circuit. So what I have, this part you can simply have this RD into this part you have already, and this part of the circuit is represented. This part is represented by means of its Thevenin equivalent resistance and Thevenin equivalent voltage. So what was that? You have V in 1 there and 1 upon GM1 there. Now the circuit looks somewhat easy to deal with. So can you identify what is this? What is the configuration for this particular circuit? It's a common gate. So it's a common gate. So you know what should be my output voltage? How to calculate the output voltage? Because at the source you applied some voltage V in 1 with some source resistance 1 upon GM1, and you have this RT over there, the drain resistance. So the formula is pretty simple, as you know. This is nothing but V out 1 upon V in 1. What is that? It should be V out 2. There's a mistake. It should be V out 2. This one. This is not V out 1. This should be V out 2. This is V out 2. Right. So what is your V out 2 upon V in 1? Simply common gate. So there is no phase reversal. RD upon 1 upon GM1 plus 1 upon GM2. Right. 1 upon GM1 plus 1 upon GM2. That means 1 upon Gm of the amplifying MOS plus the this particular source resistance. So RT upon 1 upon Gm1 plus 1 upon Gm2. Okay. So that is the expression for V out 2 upon V in 1. Now if I assume that both of these two transistors they are equivalent, they are same. So in that case they share the equal property, then Gm1 and Gm2 they are same. That is equal to Gm. Then what I find? V out 1 upon V in 1 already I have obtained in the last slide. Minus RT upon 1 upon Gm1 plus 1 upon Gm2.
The GM1 do है ना ये क्या कॉम्बिनेटेड
If you don't have any RS, you have RS, you have the source resistance. Source resistance present. It is 1 upon Gm1. If that is 0, then simple Gm1. If that part is 0, I mean, if you don't have this part, then simple Gm1. Right. So what is your V out 1 upon V in 1? Minus GMRT by 2. What is V out 2 upon V in 1? GMRT by 2. Okay. So V out 1 minus V out 2 when V in 1 is acting alone is given by minus GMRT into V in 1. Similarly, now that part we have done, and then we can invoke this similarity concept that when V in 2 is acting alone, then instead of having this negative sign, what you have V out 1 minus V out 2 is nothing but GMRT times V in 2. Right? So we have done this calculation with V in 1 acting alone. And by virtue of symmetry, we can come to the conclusion when V in 2 is acting alone, what should be my output voltage? V out 1 minus V out. What is my differential output voltage? And then ultimately, when both V in 1 and V in 2, both of them are present, both of them are active, then what is my output voltage? V out 1 minus V out 2 is nothing but the superposition. If we apply the theorem of superposition, so you have over here when V in 1 is acting alone, then it is minus GMRT V in 1. When V in 2 is acting alone, then GMRT V in 2. So when both of them are acting, that is minus GMRT V in 1 plus GMRT V in 2. That means minus GMRT within bracket V in 1 minus V in 2. This much. When both of them are acting. Right? So what is the differential gain? V out 1 minus V out 2 upon V in 1 minus V in 2. So one thing that minus GMRT that you have already obtained using this half circuit concept. So using the half circuit concept, you can come to the same conclusion, but at a much easier mechanism. But if you use this theory of superposition, then you also come to the same conclusion. But this particular analysis is even more exhaustive analysis. Okay. So then this part I would like to mention over here. So suppose you have say a common source stage like this. You have a common source stage like a single stage common source amplifier like this, and you have a differential pair like this. Both of them are biased using a fixed current source, constant current source, that is ISS. But remember the GM value that you are getting, both the cases are not the same. Why? Because you know that is expression for GM square root of twice IT lumency of W over L. Even if both of them are sharing the same value of W and L and same lumen, same Cox, still since this particular MOS is carrying this entire ISS, and here this MOS M1 and M2, each of them they are carrying half of this ISS under DC condition. So therefore, that GM over here and this GM as we obtained from this differential pair, these two GM are not same. In fact, the differential pair, the GM that you are getting using this differential pair, that GMD if I call, GMT is nothing but the GM with the single stage divided by root 2. Although it seems like okay, the same gain you are getting, but it's not actually not the same gain. Right? Suppose you have got this one, you have got this particular circuit, and then suppose you would like to make it differential pair so that you by another MOS like this, another resistance like this, and connect like this. Then as soon as you connect, then the GM value drops. You will not be getting the same gain. Although mathematically it seems that minus GMRT, but remember whenever you connect the another stage of amplification over there, not the stage. I should state that it's not a stage, rather another pair of amplification. One stage and another pair of amplification. Then your GM electrons. This GM is not the same GM, this GM upon 2. Okay. Okay, fine. So, obvious. I have not even discussed anything regarding body electron. None of the segment. None of the segment. Neither are not nor body effect, nothing. And I can assure you that in your examination also, this part will not be there. Only this simplistic. You understand what is body, what happens for body effect if I apply for a single student. You have already done this in the last class. Okay, but it should be there because source is not at fixed voltage. And moreover, you understand that here we consider that this ISS is a constant current source, ideal current source. Ideal current, right? But typically this cannot be ideal current. As of now, we have discussed everything in terms of ideality. That means these two resistances, they are same. These two MOS, M1, M2, they are having this equal property. This ISS is also an ideal kind of thing, ideal current source. But remember, all this ideality, all these assumptions, power. Okay, so let's have a look at the non-ideal behavior of the differential. We have already seen some ideal behavior. That means both of these two resistors are same, RT and RT, and you have the current source, that is ideal one. This current source is ideal one, ideal current source, and these two MOS, they are also having the same property, same GM, everything same. Now let's assume that let's incorporate some non-ideality into the circuit, and let's find out what happens. So first of all, what I do, say this current source is not an ideal current source. So if it is an ideal current source, then you understand that resistance from here to ground, that resistance is equal to infinite, right? But if it is not ideal, then obviously you have to incorporate some resistance RSS corresponding to this I square, which is large enough, but still you have to incorporate something over there. Now, once you do that, and then if you perform this common mode analysis, then what happens? Then for this one, that's it. So now, for the common mode analysis, what happens? If you have some change in the common mode level, then obviously the output side also. Now what I find for this particular case, for the common mode analysis for MOS M1 and M2, the gates are connected together, sources are connected together, and if both of these two resistances are RT, so you can expect that you have the same current flowing through this RT and RT. So what about V out 1 and V out 2? They are same. So what I can do, I can have these two. So their gates are connected together, sources are connected together, and the drain potentials are also same. So I can visualize that, okay, these two MOS are there in the circuit in parallel. Gates are connected together, sources are connected together, drains are connected together. So they are in parallel, right? So I can simply, instead of having two MOS devices M1 and M2, I can simply observe their behavior by using a single MOS with twice the width. Because if I have one MOS, I'm just observing this top view. Another MOS. Suppose this is D1, S1, this is D2, S2, and this is the gate, and these two gates are connected together. What happens if these drains are connected together? If drains are shorted and sources are shorted, this is the length, same length, and these are the individual widths. Now, if they are connected together in parallel, then what happens? The width gets doubled. W becomes 2W, right? And individually, what happens? Individually, when this M1 and M2 they are acting separately, then you have half of the current flowing through each of them. And now, if you observe this M1 and M2 combination as a single MOS, M1 plus M2, then what is the amount of current? Twice double, right? So the expression of GM, you know, what was the expression of GM? GM is given by square root of twice ID mu n C of W over L. Okay. Now, when you consider this combined MOS M1 plus M2, for which the current ID gets doubled, right? If you have ISS by 2, ISS by 2, here it is ISS, and the widths are also double. I mean, if you consider this width for M1 is W, width for M2 is W, width for M1 plus M2 is W. Double. So now for this particular case, GM M1 plus M2, for which case so this ID gets doubled and this W gets doubled. So therefore, this GM M1 plus M2 becomes 2GM. Yeah, 2GM. So now this circuit reduces to this one only. This MOS M1 and M2 is replaced by a single MOS with double width and GM given by twice GM. You have this drain and this drain, they are shorted, same voltage, they are shorted together, and then you have from here to VDD you have RT parallel. So what is effective resistance? RT upon 2, right? And you have RSS there between source to ground. So therefore, if you have some change, if you experience some change at the gate over there, you have the corresponding change at the output also. And that change and that ratio, this V out upon V in CM, is known as the common mode gain of this particular amplifier. Common mode gain. That means if you have some change over there, that means if the common mode level experiences some variation over there, it is also reflected at the output voltage. And that common mode gain over here is nothing but, if you simply apply, it's nothing but a common source stage source degeneration, is nothing but minus RT upon 2 by 1 by 2 GM plus RS6 as you know. Okay, and now the most important part is that if you incorporate some kind of non-ideality, as we have already mentioned, some non-ideality. For example, suppose these two MOS devices, they are not sharing the same property. As of now, we have experienced that, or we have assumed that both of these two MOS devices, they have the same threshold voltage, they have the same W/L ratio, they have same nuance of. As a matter of fact, they have same GM, but sometimes these two MOS devices, M1 and M2, might not be having the same GM. They can have different GMs. Now, if they have different GMs, then what can happen over there? Suppose both of them are experiencing same gate source change, but if the GM values are different, you don't expect the same current is flowing, even if they are subjected to common mode signal. That means both of these two MOS devices, their gates are connected together, their sources are connected together, so you have the same gate source change for M1 and M2, same gate source change, but their GMs are different. Because these two MOS, now let us incorporate some non-ideality into our discussion, and let's assume that these two MOS devices, they are not same in terms of their properties. We have different GM1 for MOS 1, GM2 for MOS 2. So therefore, even if they are subjected to same gate source variation, you don't expect the same current flowing through them. So therefore, this voltage Vout1 and this voltage Vout2 will not be same, even if they are subjected to same gate voltage. That means this Vout1 minus Vout2 now it will become non-zero, even if we have established the equilibrium condition. We have already obtained that if V0 is equal to V2, that graph you can remember, that graph that we have already drawn, this graph. So if V out 1, so this one, as you know, V in 1 minus V in 2, and this one is V out 1 minus V out 2. So we have already noticed that when V in 1 minus V in 2 is equal to 0, that means you are over here at this particular point, that means V out in that particular case, V out 1 minus V out 2 is also equal to 0. That means if you don't have any change in the gate voltage, that means both of them are experiencing the same gate voltage. In that case, the differential output was 0 because it's a differential amplifier. It is not sensitive to any common mode change. But here you see that if this particular configuration, in this particular architecture, these two MOS devices M1 and M2, they have the different set of GM1 and GM2. In that case, even if we apply some common mode signal over there, it will be having some non-zero differential output. That means if some change is present in the common mode signal, then the differential amplifier, this particular pair, will identify that change as differential change, and accordingly it will produce a differential output. And this is known as the common mode to differential gain. Right? And the differential gain and common mode differential gain, so you must understand that gain should be ideally this common mode to differential mode, that gain ideally should be 0. But eventually, if you incorporate this kind of non-identity into your structure, in that case it will never be 0. Right? And the differential gain upon this common mode differential gain, their ratio, and hopefully you know the name of this factor, it is known as the common mode rejection ratio, CMR. Now we are in the process of calculating this CMR, common mode rejection ratio, but hopefully because the calculation is little bit tedious and little bit hectic, so hopefully we will discuss this one in detail in the next class.